I'm going to do a quick tutorial where we have two samples, but now it's independent samples. We're doing independent data here. And this time I'm going to use the classical method. I just finished an example where I used the p-value method when it was dependent data. So the same sets of data, except I pretended they were from something different up here. Down here, you can copy these all down if you want and follow along. Probably have to pause it to get them all in time. Down here, we're going to change the scenario. We're going to say, all right, before I just had 30 boxers, and this was one guy's right hand, this was one guy's left hand, this was one guy's right hand, this was one guy's left hand. Now what I'm going to do is I'm going to go out and I'm going to choose 30 boxers at random and measure the power of their right hands and write those here. And then go out and choose 30 other guys at random and measure the power of their left hands and put them here. So that's what I did here. I'm going to pretend that's where this data came from down here, and that difference makes it independent. The fact that me choosing some guy here and measuring his right doesn't force me to choose a specific person over here. It's a completely different person over here. This is independent of this. It means that I have independent data. And what you'll see, I'm going to keep comparing this back to the dependent data example. A few things change. The main thing is that up here we just changed, we didn't even do two sample stuff. We had two samples, but we kind of made a third set of data and then just tested that one set of data to make it kind of one sample testing, to make it a t-test. Down here, we're not going to do that. We're going to use these two sets of data. So our null and alternative hypotheses will be a little bit different. I guess this is as good of a spot as any. Up here, we compared mu of the difference with 0. That's not what we're going to do here. Down here, we're going to compare our two different mu's, because we have two mu's. We have a mu for the right hands, and we have a mu for the left hands. So mu sub r, mu sub l. We're going to compare those two. So my null hypothesis will be that they're the same, and then my alternative hypothesis, which will also compare those two, I'll have to read the problem. And here it says test the claim that the power differs. Differ is a key word here. It means does not equals. If I said test the claim that the power of the rights were bigger than the power of the lefts, I'd put greater than here. If I said less than, the power of the rights were less than the power of the lefts, I'd put less than there. But in this case, I said differs, so I put does not equals. Okay, so I got my null and alternative hypotheses. Because this says does not equaled here, I have a two-tailed test. Again, just note the difference between dependent data and independent data. Even your null and alternative hypotheses are different here. All right, now, I guess to follow along, what I got to do is state the shape, the center, and the spread of my distribution. The shape, it better end up being approximately normal because that's the only thing we know how to study in this class. It does. It's approximately normal. However, the reason why is a little bit different. Up here, we really only had one sample to deal with. It was this difference column. So we said, okay, the number of observations in that difference column, 30, was greater than or equal to 30. Down here, it's a little bit different. We have two different columns, and they could have different number of observations in them. In this case, we have the same, but there's no reason I couldn't get 50 boxers and test their rights, and then 40 boxers and test their lefts. That's the nice thing about independent data is that you don't have to have the same amount of each of them. So my criteria for being approximately normal is I'm going to need the number of observations in my right column to be greater than or equal to 30, and the number of observations that measure the left hand to be greater than or equal to 30. And in this case, they both are, so it's approximately normal. Center. Okay, similar to up here. Up here I said the center is 0 because mu naught sub d, kind of what I expect this column to be right here, is 0. Down here that it's also going to be 0, but for a different reason. It's because mu naught of my rights minus mu naught for my lefts is equal to 0. So really, mu naught, the null hypothesis, says these two things are the same. So the difference between them should be 0. And the spread, which I'll denote as sigma, and then down in the subscript, this is going to get kind of annoying, x bar of my rights minus x bar of my lefts. You don't have to know that notation, but I don't know. Anyways, what that's equal to, okay, we kind of have a decision here. We have a standard deviation we can get from this column, and we got a standard deviation we can get from this column. We could calculate those, we will, or our calculator will. Which one do you use? It turns out you don't use either of them. You use kind of a weighted average of the two. So what we're going to do is we'll take the standard deviation of my rights, and then I'll square it to make it the variance, and then I'll divide it by the number of observations I have in my rights, and then I'm going to take the variance of my lefts, so the standard deviation of my lefts squared, and divide that by the number of observations I have in my left. And what that will do is give me a weighted average between the standard deviations of these two columns. The reason, again, that's important is because we could have more observations here than we have over here. So we want to make sure that we weight them accordingly. And that's something you could calculate if you want. I don't really care that you calculate it. You can leave it just like that for my purposes. Show me you know how to get it. But your calculator will come up with these values, as I'll show you later. Now what we want to do, draw a picture, make our conclusion, and be done with this. Sure, that's approximately normal. Using approximately a little bit loosely. Maybe I should try again. That's a little better. So I have this distribution. It's approximately normal because that's what it says up here. The center is 0. Again, that's kind of what it says up here. And then it's got this spread, whatever this number is. And so what I got to do is figure out the values that go in here. If I were doing the p-value method, it would be easy. I could just do that right now. But since I'm not using the p-value method, and I'm using the classical method, I need to first set up my rejection regions. So I need to pull up some t-tables. So hang on a minute. Here are some t-tables. Let me make sure that's within your view. It looks like you can see that. So what I got to do is figure out my critical regions. I got to set up my rejection region. Got to find my critical values. And the way I'm going to do that is I know that I have a two-tailed test here. And I know that alpha is 10%. So the total area of my rejection regions has to be 10%. I got two of them, one over here and one over here. So for them to in total have 10%, I need 5% over here, and I need 5% over here. If you happen to have the inverse t function on your calculator, you can figure that out by doing inverse t 0.05 and then 29, because that's how many degrees of freedom we have. 1 minus n. What we're going to do on these, since we have two different values of n, is we're always going to use the smaller of the two. In this case, they were both 30, so it didn't matter. But if we had different values here, you just use a smaller one. So anyways, what I am going to do, since I don't have that function on the calculator here, is go down to 29 degrees of freedom and then say I want 0.05 to be the tail probability. And it looks like I get 1.699. 29.05, 1.699 right here. So what that means is this value here is I guess really that value should go down here, 1.699, and this is negative 1.699. The way I've been doing things is I've had z-scores in a bottom row and kind of the x-scores up here in the top row. So now I have my critical values. I can go do my test. If I go over here, it's underneath stat, go over to tests. This time we're not going to do t-test because we have two different samples. So it's either this guy or this guy. We don't know sigma. Nowhere in here does it say I know the standard deviation. Somehow I know the standard deviation of everybody's right hand power. So I don't have sigma. I have to use two-sample t-test here, the fourth one. And then I can either put in statistics about the data or the data itself. In this case, I have the data itself. I got the right hands in L1. I got the left hands in L2. I'll leave both the frequencies alone. And my alternative hypothesis is that the right hands do not equal the left hands. Pooled, you can just leave that as no. And then we're going to calculate. So when we calculate here, what we do is we get a test statistic, this 2.86. And 2.86 is in the rejection region. It's way the hell over here. So really what the 2.86 was is it's the difference between these two x bars, the 71 minus the 57. So if you really wanted to figure out what the difference between those two were, it would go up here above this guy. I don't care that you do that. And if you really wanted to figure out what the spread was, you could use, here's the standard deviations, divide them by the values of n. If we scroll down, it'll give us those n values. So you can work backwards into all this stuff, but I don't care that you do it. All I care is that you have a picture of something like this, and then you say, because the test statistic is in the rejection region, Maybe because the test statistic, which in this case was 2.86, is in rejection region. There is sufficient evidence. It's annoying to write with the stylus. I don't know if you've ever tried it. Evidence to reject the null hypothesis and conclude that power differs between hands. So I'm not concluding that the rights are better than the lefts, even though that's kind of what the data indicated, because my claim was that it differs, and there's plenty of evidence to conclude that it differs. So that's my conclusion. There's my picture. That's the end of this example.